Hi everyone, today we are going to talk about maximum likelihood estimation in GLM. In particularly, we are estimating the model parameters beta, just like what we do in classical linear models. We are interested in getting these beta so that we can either do model inference or some predictions. Before we start our derivation on this beta, let's look at some of the facts that we've covered in the previous two videos. So the first one is the three components in a GLM model. So you have your random part, which are independent yi's, I from 1 all the way to n. So each y, they follow the same kind of distribution. That's part of the exponential family, but they can have their own parameter values. The second part of the three components is the systematic part, which is basically a linear combination of different covariates and the model parameters beta, just like in your classical linear model. And then the third part is the link function. So it serves as a bridge that links the random component with the systematic component. So mu I is the mean of the random component, and then eta I is just the systematic component in the linear model. If you have some questions about these three components, please refer to my first video. And we will also use two other results that will be part of our derivation. So the first one is the mean of yi, we denote as mu I, is actually equal to the first derivative of b theta I. And then the variance of yi is equal to b double prime theta I and a phi. So these two conclusions, we've derived them from some facts about maximum likelihood. So you can go check out my second video. I give a very detailed proofs. Okay, so let's start with today's topic. We are interested in estimating beta, and we will use maximum likelihood method. So if we write out the likelihood as L beta, we basically want to find beta that maximize this likelihood. And we know that the total likelihood is equal to the sum of each individual likelihood, meaning the likelihood for each observation. And this capital, actually I should be using lowercase l just to be consistent with my previous notations. Lowercase means log likelihood, right? And uppercase is just the likelihood. So this will be the log of uppercase Li, and we have the uppercase Li right here. This is our likelihood, and then we have to write it into log version, which means we drop this exponential part. And because it's a sum, we can write it as the sum from I to n yi theta I minus b theta I a phi plus sum I from 1 to n c yi phi. Okay. In order to maximize the likelihood, we are going to take derivative. So dl beta d beta j, because this beta can be a vector of betas it's a vector of parameters for each of the covariates we're interested and also the intercept. So that's why here we only look at beta j, the jth beta, and we can generalize that to all the betas. We know that to maximize likelihood, we want the first derivative of the likelihood to be 0. So we are solving for a beta that makes this derivative to be 0. And a natural question you might have is, well, I don't see a beta in my likelihood function. How can I take derivative? Remember, in a generalized linear model, beta naturally exists in the systematic part. However, we use a link function that connects the systematic part, which contains the beta, with the random part. So they are actually interconnected. So even though you don't see beta directly from this expression, but because the fact that beta are connected with yi through the link function, and that's how we're going to find the derivative with respect to beta. We're going to find it through the derivative with respect to other parameters that we see in this likelihood. So we apply chain rule here. So in order to get this derivative, we will do something like dl d beta j equal to dli. The first time I saw this equation, I was very confused. I didn't understand why you would go from a very easy derivative, dl d beta, into such a complicated chains of derivative. Now I will give you I will walk you through the process of building up this chain. First of all, naturally, as I pointed out, we don't see beta here, but what do we see? We see theta I here. So the first thing we can do is take the derivative of the likelihood with respect to theta I, since it's physically present in the likelihood. And then what will be the next step? If you look at the two results that I mentioned in the beginning of the video, you will see I connect theta I with mu I. We know how to express theta I if we know basically the expression of the likelihood, right? So we can do d theta I d mu I. That shouldn't be hard based on this equation. And then mu I is part of the random component. It's the mean of random component. And I emphasize this a couple times. Link function connects the random part with the systematic part. So now the third derivative will be something that connects the random part with the systematic part. And we know it has to be d mu I in the numerator so that you can cancel them out and make sure it's equivalent to the left-hand side. And in the denominator, we will give the systematic component, which is the eta I. And then the eta I, the beta j will be very natural because we know eta I is equal to sum of xij beta j, right? All right, that's some intuition behind this chain rule. Now let's do it part by part. For the dl, dli, d theta I part, we are just going to take the derivative with respect to theta I from this L beta, and that should be fairly easy to do. We will have yi minus b prime theta I divided by a phi. A phi is a constant with respect to theta I. Okay, and you might ask me, there was a summation, but why you're dropping the summation here? Because if you look at the footnote, I am calculating one likelihood at a time. Essentially, the sum of the Li, the beta will be 0 on an individual base. That's easier in representation. The next part will be the theta I, the mu I. And what do we know about this part? Here we are going to apply this equation 1. Since mu I is equal to b prime theta I. So what we can naturally get is d mu I d theta I, which will be b double prime theta I. And by some rules of calculation, I'm just going to tell you d theta I d mu I is equal to d mu I d theta I inverse. So that's going to be 1 over b prime theta I. Okay? And then the third part is d mu I d eta I. What do we know about this part? Well, we know that g mu I is equal to eta I. So eta I, mu I is equal to g inverse eta I. I can do this step because I know g is a monotone function. So the inverse exists. And it's a one-to-one function. This part, let's just leave it like that because depending on what distributions your y follows, you have different link functions, and different link functions will use different results for the d mu I d eta I part. Okay, so let's just leave it like that. Then the last part, d eta I d beta j. This should be very easy because eta I is equal to sum of beta j xij j from 1 to p, let's say. So when you take the derivative of this linear combination, only xij will be left. All the other xi are not related to beta j. Okay, now let's put everything we have together. So we will end up with dli d beta j equal to this first part yi minus b prime theta I a phi, and then the second part, which is 1 over b double prime theta I, and then the third part, let's just leave it like that because it depends on what link function you chose, and then xij. Alright, we can do some further simplification because the equation 2 tells us b double prime theta I times a phi is equal to variance of yi. We can substitute this part as variance of yi, so we can rewrite it as yi b prime theta I divided by variance of yi times d mu I d eta I, and we can put this xij here. Also, if you don't like this b prime theta I, you can substitute it by mu I according to equation 1. So yi minus mu I xij variance yi d mu I d eta I. Well, that's pretty neat. Now we have to summing over the n observations. This is just for the ith observations. We want the total likelihood. So if we summing over nth observations, all we need to do is put a summation in the front from 1 to n, and then we copy down what we have arrived in the previous step. Don't forget, we are solving an equation here. We are solving that the sum of the likelihood is equal to 0. That's what we are solving here. Sorry. Let's look at some examples. In the binomial case, in the previous video, I've shown you that the parameter pi I is equal to mu I and equal to a link function g of eta I. So d mu I d eta I, the part that's depending on the g function in the binomial case, the CDF of standard normal distribution, if that's our link function, then the d mu I d eta I, since it's a CDF, it's going to be equal to phi prime eta I, and the derivative of a CDF is just a PDF, and we use this lower phi to denote a PDF of normal distribution. Okay, we also know variance of yi is equal to pi I 1 minus pi I divided by ni, because in binomial distribution you essentially have two parameters. One is pi I, the probability in each trial, and how many trials you've done. So that's ni. So variance is equal to this. And let's put everything back together into the estimating equation. All I did was substituting each component in the equation, and that's what I get. You can solve for this equation to get the beta. In addition to using CDF as a link function, it's also common for we to use the logit link, which is eta I equal to log pi I 1 minus pi I. And in this case, we want the d mu I d eta I. It's easier to get the eta I d mu I, and we can inverse this d eta I d mu I to get d mu I d eta I. So this is going to be 1 over pi I 1 minus pi I. This is just some algebra, so it might be easy to rewrite it as log pi I minus log 1 minus pi I, and if we take derivative of this whole thing, so if we do d this over d mu I, in binomial we use pi I, mu I is equal to pi I, so that's why we're essentially doing d pi I, and that's going to be 1 over pi I minus 1 minus pi I, and another layer of negative sign because of the negative 1 in front of pi I, and that is 1 over pi I minus plus 1 minus pi I, 1 over 1 minus pi I, and that's exactly what we have here, pi I times 1 minus pi I. So that's how we arrive to this value here. And because what we need in the estimating equations are the mu I, d eta I, so we do the inverse of that, so that's pi I 1 minus pi I. So in this case, we have the estimating equation looks like this. Ni yi minus pi I xij. This is the dli d theta part. This part doesn't change, and this is the d eta I d beta j part. That part remains the same. We have the variance of yi and the d mu I d eta I, which is pi I 1 minus pi I, and we can cancel out these two. So it's a lot easier than the normal link, ni yi minus pi I xij equal to 0, and the likelihood equations finally simplify to the estimating equations that I just wrote. So you might ask me, where is beta I? Where is beta j in this equation? We were estimating beta j, but I don't see beta j. Okay, so because beta j is equal to mu j, and mu j is equal to g inverse eta I, and eta I is g inverse sum of beta j, xij, j from 1 to p. Okay, so that's how you plug in this part back to the pi I part in order to get beta j into the estimating equation so you can solve for beta. Before we end this video, I want to show you real quick how we put this estimating equations into a matrix form. The first thing is to substitute this d mu I, d eta I part. As I said, this depends on the g function, and it's actually 1 over g prime mu I, because d eta I d mu I is equal to g mu I prime, right? So the inverse of d eta I d mu I is d mu I d eta I. So we need this. How do we write a summation back to a matrix representation, or how do we do it the other way around? Let's start with an easy example. Imagine we are doing x transpose y. If we were doing this, and let's say our x was a vector, and because it's a transpose, so it looks something like this, and our y is a vector, that's x transpose y. And when you are actually doing the calculation, you're doing it by summing up the product of x1 and y1, and then x2, y2, you're taking the sums of these products. So we can also write it as xi, yi, I from 1 to n. That's how we convert summation into matrix form. Similarly here, this yi, if we look at all n's yi, it's still going to be a vector. So we will have y as what it was in the example I gave you, and then we will do the transpose of x matrix, because they're going to be, so this x transpose will look like x1 transpose, x2 transpose, depending on how many observations we have. So that's our x transpose. And in the y part, we are it's not simply y, we also have minus mu. And then what's in the middles are two diagonal matrices. What are they? So V is a diagonal matrix with 1 over variance of yi on the diagonal. So 1 over variance of y1, 1 over variance of y2, all the way to 1 over variance of yn. That is our V. V inverse look like this, which means V is diagonal matrix with variance of y on the diagonal. How do I know it is a diagonal matrix? This has to do with the assumptions we made for the random component in GLM. If you remember, we said yi, they're independent. So the covariance of any yi and yj are going to be 0. That's why the off-diagonals elements are all 0. Okay, so what is this delta inverse? Delta inverse is, again, a matrix with diagonal element of 1, g mu 1, g prime mu 1, 1 over g prime mu n. And that corresponds to this d mu I d eta I part. Again, we are setting it to 0. And it is going to be a function of beta, and we usually use this u to denote the function of beta. There's a reason why we single out the variance and the g prime mu I. It might seem to be odd at the beginning, but if you know about canonical link, for any link function that's canonical link, v and delta, they cancel out each other. So we can further simplify this u beta into u beta equal to x transpose when mu equal to 0. The next video will be about canonical link. Okay, that's all I have to say about maximum likelihood estimation for GLM model. If you have any questions, please leave them in the comments below. Thank you.